Alright, so we're going to write the reaction for the alpha decay of strontium. We can do this for any particle, but just randomly pick strontium. So the first thing you want to do is you want to start with what you know. It's strontium, and we're going to fill in the information for strontium. Now, lower left-hand side, I usually like to write the charge, the nuclear charge of strontium, which is 38. You can get that from the periodic table. The upper left-hand side, I'll put the mass of strontium. Now, strontium's mass can vary. I'm just going to pick a particular type of strontium. We'll call it strontium-87. Right? And then in the upper right-hand side, I'll put the lepton number. Now remember, all particles have a lepton number of 1. All antiparticles have a lepton number of -1. So strontium is indeed a particle, so I'll put 1 up there. Make that nice and prevalent. Okay, so then what I want to do next is look at what kind of decay is this. This is alpha decay, so we're going to produce an alpha particle. So on the right-hand side, the first thing I want to do is write down an alpha particle, which is that symbol right there. Then I need to know what the charge of an alpha particle is. Charge of an alpha particle, because it has 2 protons, is +2. The mass of a alpha particle is 4, because it's just 2 protons and 2 neutrons. And then because it's a particle, it also has a lepton number of +1. Okay, so then the way to balance these, I like to go in this particular order. You don't have to go in this order, but I think it helps to do this order. I want to balance the charge first. So what I need to do is I'm going to find out what sort of particle would balance this out. Over on the left-hand side, I have a charge of 38. The right-hand side, I have 2, so what plus 2 equals 38? Well, that's going to be 36. So then I look at my periodic table, and I find out which particle has a nuclear charge of 36, and that's krypton. Not kryptonite, like Superman, but just krypton. Alright, so then the charges are balanced. 38 equals 2 plus 36. Check. Next step, I'm going to balance the mass. Now, the mass is 87 over here. That means the mass on the right-hand side has to be 87 as well. Well, 87 does not equal 4. It equals 4 plus something else. That something else is going to be 83. So I'll put 83 up here. That's going to be the mass of krypton. Now, krypton actually has an average mass of 83.8. That just means that some kryptons are 84, some kryptons are 83, but on average, it averages out to 83.8 because there's going to be a little bit more krypton 84. But that doesn't mean we can't make 83 mass krypton. We just got a little bit lighter krypton here. So, charge is balanced, mass is balanced, check, check. Now, the last thing we need to balance is lepton number. The lepton number right on the left-hand side is 1. The right-hand side is 1. Well, actually, krypton is also a particle, so we'll put +1. Lepton number on the right-hand side is 1 plus 1, which is not equal 1. So we need to put something else over here that has a lepton number of -1, so that means the lepton numbers are balanced then. So I'll put something with a -1 over here. And that particle also has to have a mass of 0 and a charge of 0, because otherwise we'd have to add more particles. So 0, 0. We're going to add in a particle that has a mass of 0, a charge of 0, and a lepton number of -1. The only particle that matches that is an anti-neutrino, which is that symbol right there. So now everything's balanced. The charge is balanced, the mass is balanced, the lepton number is balanced. That's done. Now something else that's kind of neat to note is that particles and antiparticles, when they meet up, they're going to annihilate each other and produce energy. Right here, we have an antiparticle, an antineutrino. That antineutrino, when we create it, is eventually going to trickle off on its own little adventure and meet up with some other random particle, and it's going to meet up with that particle and annihilate each other. They're going to cease to exist. They're going to produce energy, radiation. All right, and the amount of energy that they produce is going to equal E equals mc squared, where the mass would be just the mass of the antineutrino plus the mass of what other particle met up with and annihilated. Now also the charges have to balance out too, so it's going to meet up with some sort of chargeless particle, and they would annihilate each other that way. So we can actually figure out how much energy is produced in this nuclear reaction based on that. So now let's go to beta positive. Beta positive reactions, we're going to do it with carbon 14. Now there's different types of carbon. One of the more unstable types of carbon is called carbon 14. It's just a little bit heavier carbon. So I already filled in the information for beta positive. We're going to go through the same process. The charge of carbon, nuclear charge of carbon is +6. The mass of carbon 14 is 14, and then the lepton number is 1. So first thing we want to do is we want to figure out what is a beta positive particle. Well, it's basically a positron. Now the symbol for a positron is an E with a plus next to it, but you can also write B for beta. Beta particle, sometimes you'll see that for a beta particle, because E plus beta, same thing, okay? Now, with this beta particle, we already know information about it. It's a positron, so it's going to have a +1 charge. Its mass is essentially 0. It's not quite 0, but it's pretty close to 0. And it is a antiparticle because it's a positive electron, so it's a lepton number of -1. So then we're going to go through, we're going to, now that we have that information filled out, we're going to balance the charge first. So on the left-hand side we have 6, on the right-hand side we have 1. 6 does not equal 1, but 6 plus, or 1 plus 5 equals 6. So I'm going to put in something that has a +5 charge, nuclear charge, and that +5 thing is going to be boron. Don't get that confused with the beta particle. It's a B instead of a beta. Okay. Now, next thing we want to do is balance the masses. Now, the mass is 14 on this side. On the other side, it's 0. So we're going to have to put a 14 here. Now, we're going to notice something. Boron 14 is not very stable, which means that this reaction is probably not going to happen, or it might break off a couple of neutrons in the process. And those neutrons will just go on to do other things, like combine with other things. And then, but anyway, just balancing this reaction. Boron is a particle, so its lepton number is 1. Finally, we're going to balance the lepton number again. Left-hand side is 1, right-hand side is 0, because this is -1 plus 1, so we need to have another particle here that has a lepton number of 1, a mass of 0, and a charge of 0. And the only particle that matches that is a regular neutrino, which symbol is nu, or it looks like a V. Alright? So now the charges are balanced, the masses are balanced, the lepton numbers are balanced, and so the whole thing is balanced. Now this beta particle, this positron, if you will, it's not stable. I mean, it's an antiparticle. It's going to go along and probably meet some electron that's nearby, and it's going to meet up with that electron. An electron is negative charge, a positron is positive charge. One's a particle, one's an antiparticle. They're going to meet up and they're going to annihilate each other. The charges cancel out, and we're just going to produce energy again in the form of E equals mc squared. And the way to figure out that energy is we would just take the mass of the positron plus the mass of the electron, basically just double the mass of the electron because they have the same mass, and we can figure out how much energy this reaction has. Now let's try a beta negative reaction for carbon 14 again. So this one actually is very common in nature, and we'll come back to this one later. But carbon is already filled out. The charge 6, 14 the mass, and lepton number 1. And a beta negative, what it's going to make, it's going to make an electron. An electron is actually going to be released from the nucleus. Even though we don't think of electrons as being in the nucleus, they can be created in the nucleus and be released. It's kind of weird. But I'm going to write down an electron, use a negative sign next to it, and fill in the information for an electron. Now, an electron has a -1 charge, a mass of essentially 0, and it's a particle, so we're going to put a +1 for the lepton number. So then, I'm going to go through and figure out what does this make. Well, first thing I want to do is balance the charge. The charge is 6 on this side, -1 on this side, so I need to add 7 to this side because 7 minus 1 is 6. So I'm going to add 7 in red here, and we're going to get nitrogen. Now this reaction actually occurs quite a bit in nature. This is where carbon-14 dating comes from. Anyway, so now and I'll put the lepton number of nitrogen, that won't change, it's a particle. Now the charge is balanced on both sides, 6 equals -1 plus 7, the mass is not, 14 equals 0 plus 14. Now nitrogen wants to be 14, that's a pretty good stable isotope of nitrogen, that one's good. So now the charge is balanced, the mass is balanced, lepton number, 1 equals 1 plus 1, that's not true, we need to add a -1 on the other side. So -1, 0, and 0 because we don't want to add any charge or mass to this. And the particle that matches up with that, again, is an antineutrino. Now once again, that antineutrino is going to go along its merry little way, and it's going to react with something else nearby. And that thing is going to annihilate that antiparticle is going to annihilate that particle, and they're going to annihilate each other essentially, and produce an energy which is equal to E equals mc squared. So all of these reactions produce energy. And any energy is going to be heat, radiation, light, things like that. Now the next reaction we're going to talk about is nuclear fission. So nuclear fission is when the nucleus starts off as a really, really big unstable nucleus. It's really big. And it breaks apart into smaller, more stable nuclei. So it can break it into like 2 nuclei or 3 nuclei or 10. It's going to produce a lot more smaller and stable nuclei. So we're going to start with uranium. Uranium has a nuclear charge of 92, mass of 238, and a lepton number of 1. Uranium is a very unstable nuclei, and it's used a lot in fission reactions for nuclear power plants. Now, you'd have to be told more information to balance this reaction. So maybe uranium breaks apart into something else, like iron. Iron is the most stable, so it's going to eventually want to get to iron. So let's just put iron in there. Iron is Fe. And then we would just fill in the information for iron. So we'd have 26. And then it would say like iron 56 or something. And then the lepton number would be 1. So now we would go through the process and try to figure out what else does it make. So with a fission reaction, you'd have to be told more information, like it makes this one particle plus something else, okay? So now we go through the same process and balance out step by step. So we're going to start by the charge. 92 does not equal 26. 26 plus something equals 92. It turns out that 26 plus 66 equals 92. So I need to put a 66 for a charge here. Well, the only thing that has a nuclear charge of 66 is dysprosium, which is just simple for dy. So that's the other particle it would make. And then this particle would probably go along and decay or react again to produce something even more stable. Eventually everything's going to try to get to iron. Now these things take a long time, but we'll get back to that later. Now the charge is balanced, but the mass is not. So 238 equals 56 plus blank. Well, if you do the math, it would be 182. Now, you could put 182 here. That would work. But dysprosium, if you look at the periodic table, has an average mass of 166. That means that this dysprosium is not going to be very stable at all. So I'm actually going to put in its average mass of 166. And I'll just make a note. What's 182 minus 166? That's 16. So I'm going to put a note there. We're still down 16, okay? Now you could put 182 there if you want to. It's just not going to be a very stable reaction. And then the lepton number is 1, okay? So then we need to balance this out. So I'm going to we'll just assume that the masses are balanced now. What else do we need to balance? Lepton number. Well, 1 equals 1 plus 1. That's not true. We need to add a -1 there. So I'm going to add in something with a -1, a mass of 0, and a charge of 0. So as we know, that's going to be an antineutrino. Okay, now if you were to put now this would be perfectly balanced as long as this would be 182. Now, like I said, for dysprosium, 182 is not very stable. It's really heavy for dysprosium, so it wants to break apart even further. Well, dysprosium is going to be made up of protons, neutrons, and electrons. If it loses protons, it changes its thing. It changes its whole chemical process. It's nuclear, like what it is. If it loses electrons, it's going to just lose charge, and it doesn't want to do that. But it can lose neutrons and be perfectly fine. It can lose 16 neutrons. So what I'm going to do is I'm going to tack that on. There's 16 neutrons because here is what else is going on. So I'm going to add on to the reaction the symbol for a neutron, and now I put the values for neutrons, which would be 1 for the lepton number, 0 for the charge, and then 1 for the mass. And I would add on 16 of them. So I could do plus another one, plus another one, plus I could do plus n, plus n, plus n, or I could just write a coefficient in front. Like this. 16. That just means that I'm losing 16 neutrons. Well, now I need to go back and double check my reaction. Is it balanced now? Well, the charge is balanced. 92 equals 66 plus 26 plus a bunch of zeros plus a bunch of zeros. Check. The mass is balanced. 238 equals 56 plus 166 plus 0 plus 16 of these, 16 ones. So it's balanced. Lepton number, is that balanced? Not anymore. Because we have 1 equals 1 plus negative 1, which is 1, plus 16. That's not true. So we need to start adding some more antineutrinos, because that'll adjust it. So if I look at 1 plus 1 plus 1 is 3. Well, I need to figure out, 1 plus 1 plus 16, that's 19. 1 plus 1 plus 16 is 18. Math, right? 18 total for the lepton number. 1 plus 1 plus 16 is 18. Well, I need to add enough neutrinos to get that back down to 1. So I would add in, looks like 17 neutrinos, because then it would be 1 plus 1 plus 16, it's 18, minus 17, if I put 17 here, gets me back down to 1. Now once again, I could put 182 there and I would have been done with that reaction, but that's probably not going to be what ends up happening. Now the cool thing with a fission reaction is, once again, these 17 antineutrinos are going to go along in their merry way, and they're going to react with other things nearby and produce energy in the form of E equals mc squared. But another cool thing about fission reactions is that these 16 neutrons, they're kind of off in space, and they kind of go off like bullets. Like when this reaction happens and this loses its neutrons, it's like, I don't want you, you're too heavy, you're weighing me down, so it's going to go pew, 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 and send out these neutrons, and those neutrons are going to collide with other nearby particles, like other uranium that's nearby, and those are going to be like bullets, and they're going to kind of break the uranium apart into pieces. So it's almost like a chain reaction. When this uranium releases this, it's going to release a bunch of neutrons, which send out like bullets, and it breaks apart other uraniums, releasing even more energy. So it's like a chain reaction of energies. Look at the simulation, and I'll show you the example. Then the last nuclear reaction we're going to talk about is called nuclear fusion. So nuclear fusion is when two or more small nuclei fuse together, they come together, and they produce a larger, more stable nucleus. You can remember fusion versus fission, because fusion means fusing together, coming together, fission, breaking apart. Okay, so here's an example. We have helium, which has a charge of 2, nuclear charge of 2, and a mass of 4, and lepton number of 1, reacting with another helium nucleus. Sorry. Producing a more stable, larger nucleus, because helium is too small to be stable. So what does this make? Well, let's first balance out the charges. 2 plus 2 equals 4. So what particle has a nuclear charge of 4? Hydrogen, helium, lithium, beryllium. Beryllium. Okay? And then, that's good. Beryllium has a lepton number of 1. You can put that in there if you want to. And then, next thing to balance is the mass. So the mass of helium is 4 plus 4 equals 8. Now, beryllium usually wants a mass of 9, but doesn't mean that beryllium-8 doesn't occur. And this is almost reacted perfectly. It's going to now balance out the lepton number. Well, 1 plus 1 equals 1 plus 1. Well, what would be that other 1? Well, it needs to have a mass and a charge of 0, so that's going to be a neutrino. So a neutrino would be that last particle. Okay? So that's a balanced reaction right there. Now, with fusion, that occurs in our sun. That's how particles are created. So first hydrogen is the first elementary particle, or not elementary particle, it's the first particle fused together to make helium. Then the helium fuses together to make bigger elements, and then bigger and bigger and bigger elements. And once iron is reached, that's usually the death of a star.